Hello and welcome to today's lecture. Today we're going to look at a technique for finding a feasible solution to an integer program. We're going to look at what's called a greedy heuristic. We'll look at some different examples and we will look at the conditions under which such an approach actually returns the optimal integer solution. The topic today is not covered extensively in the textbook you have, but you will find a short note on greedy heuristics in the exercise PDF that is online. The lecture again consists of 3 separate videos. So the agenda revolves around 3 main ideas. We have heuristic approaches. What are they? Why do we need them? How do they differ from, say, an exact approach? Greedy constructive algorithms. Again, what are they? And 3 examples where we see how a greedy constructive algorithm can be used to find a solution to the problem. One of these examples is a case where the greedy constructive algorithm actually returns us the optimal solution. So we look at the reasons why that is the case there. Just like last week, there are some learning objectives I would like you to focus on today. By the end of today, I would like you to be able to do the following. I would like you to be able to understand and explain the difference between heuristic and exact solution approaches. I would like you to know what a greedy constructive algorithm is. I would like you to be able to design a greedy constructive algorithm. And I would like you to be able to give examples of when a greedy algorithm fails or succeeds. Okay, so what is a heuristic approach? Well, solving integer programs is not easy. It might be a bit counterintuitive. Integer programs only have a finite number of feasible solutions, as opposed to, say, a linear program, which has infinitely many. However, the number of feasible solutions can be astronomically large. So consider a problem with n binary variables. We can have as many as 2 to the n possible solutions. Remember, a binary variable can only take the values 0 and 1. So if I have n such variables, then there are 2 to the n possible configurations of the values of these variables. So in this case, we say that there's exponential growth in the number of solutions as n increases. If I increase n by 1, I double the number of possible solutions I may need to consider. 2 to the power of n is not a small number for large values of n, so techniques like exhaustive enumeration are not really possible. Exhaustive enumeration is a technique where we would explicitly consider each and every feasible solution, compute its objective value, and then simply pick the best one. We will look at exact approaches for finding the optimal solution to integer programs in lecture 11. Such approaches will provide you with a certificate of optimality. It might take some time, but they provide a guarantee that the solution they return is optimal. Heuristic approaches, on the other hand, are rules of thumb that can be used to find feasible solutions. So in general, they do not give you a certificate of optimality. In fact, they do not even give you a certificate of quality. So when you run a heuristic on an integer program, you have no idea how good or bad that objective value is. Of the resulting solution, at least, you have no idea how good or bad that objective value is without some other benchmark to compare to. Heuristics do have value, though. As I said, exact approaches can take a lot of time to prove optimality. So there are occasions where you need good solutions quickly, particularly in a practical setting. There you may not have the time to wait for an exact approach to return the optimal solution, and you simply want a good solution very quickly. What is a constructive algorithm? Well, as the name suggests, it's a technique for constructing a feasible solution to your problem. So they usually start out with all variables unassigned, so not a single variable in your problem will have a value assigned to it. It will then iteratively select a variable or a set of variables and assign feasible values to those variables. Feasibility here just means consistent with previous values so that you don't violate the constraints. So a constructive algorithm consists of a sequence of iterations where at each iteration you make a selection of a variable or set of variables and then decide what value to assign those variables. And at the core of these algorithms is this identification step. So how do you select the next assigned variable and how do you set the variable's value? Common techniques for doing this rely on greedy or myopic approaches. So what is a greedy constructive algorithm? Well, it simply takes the best here and now decision. So it will maximize or minimize your immediate profit or cost depending on what your objective function is. So based on the partial solution, remember the constructive algorithm is iteratively building you a solution. So at a particular iteration, you will have a partial solution. Based on that partial solution, you will greedily select the next variable. It's very short-sighted. We do not look ahead further than the current step. You simply maximize, if you're looking at profits, you maximize your immediate profit without any regard for the implications in the future. So contrast this to something like a linear programming approach, which synthesizes all constraints and variables at the same time, weighing up the trade-offs. Here you sort of sequentially choose variables and set their values. You're sort of, in effect, considering these variables in isolation, making the best decision without consideration for future implications. Typically, you don't backtrack or revise decisions. You just accept the choices maybe towards the end of the construction phase are going to be bad. Next week, we will look at something called an improvement heuristic, which relies on an initial feasible solution that we then try to improve. Okay, so usually constructive algorithms are not the sort of end of the story, but they give us a start where we can improve later. Greedy algorithms can be very difficult to design. In some cases, they don't even provide a feasible solution, but in some cases, they will actually return you the optimal solution. To illustrate how to design a greedy heuristic, we're now going to look at a small example. This particular problem asks you to determine the best set of missions for NASA to run in the coming 25 years. It's an example of a capital budgeting problem. NASA has 14 possible missions from which they can choose. Each of these missions requires a certain investment in billions of dollars, and each of these missions gives you some value in return. We're looking for the value maximizing subset of missions. Certain pairs of missions are incompatible. This just means that they cannot be selected simultaneously. These are missions 4 and 5, missions 11 and 14, and missions 8 and 9. Some of the missions also depend on other missions. Missions 4 to 7 depend on mission 3. This means that we cannot select missions 4 to 7 without also selecting mission 3. Mission 11 depends on mission 2, and this means we cannot select mission 11 without also selecting mission 2. The table here basically tells you everything you need to know. We have 14 missions listed on the left. The value of each of these missions is given on the right here. So mission 1 gives us 200 units, mission 2 gives us 3 units, and so on. Our 25-year planning horizon is sort of broken down into 5 intervals of 5 years. And for each of these intervals, there is an associated budget available. Okay, so in the first budget interval, if you like, I have $10 billion available. Each of the missions consumes some of the available budget in a subset of these intervals. Okay, so if we select mission 1, it will consume 6 of the $10 billion available in the first budget interval. Okay. Before we get on to designing this greedy heuristic, though, we are going to formulate the problem mathematically and solve it to optimality. This will give us a value which will allow us to sort of ascertain how good or bad our heuristic solution is. Okay, as I said at the beginning, a heuristic does not give you any guarantee of quality. So if we know the optimal solution, we can sort of benchmark the performance of the greedy heuristic we're going to design. Okay, so if we want to formulate this problem mathematically, what will the decision variables be? In this case, we will define 14 binary decision variables. So xj is going to be equal to 1 if mission j is selected. J runs from 1 to 14. We have 14 missions, and it's going to be 0 otherwise. This will give us the following objective function, and it should not be too difficult to see where this comes from. This is just maximizing the value of the selected missions. Okay, if I could select all of the missions, I would just collect the sum here okay, which is not really possible because I have constraints preventing me from doing that. So what constraints are there in this model? Well, here I have just listed them all for you. So the first 5 constraints correspond to our budget restrictions. There is one for each of the budget intervals we have. The first constraint here just says you cannot select more missions than the $10 billion allows in that interval. And if I look on the left-hand side of this constraint, I see decision variables that correspond to missions that, if selected, would consume some part of that budget. Okay, so the coefficient on the decision variable just says how much of the allowable budget the mission would consume. So here, if I select X1, I would consume 6 of the available $10 billion. The second block of constraints down here, these just ensure that I don't pick any incompatible missions. So you might remember that missions 4 and 5 were incompatible. And this constraint just guarantees that I pick at most one of those 2 missions. The same is true for missions 8 and 9, and the same is also true for missions 11 and 14. Down here, you see some constraints. These just model the mission dependencies. You might also recall that mission 11 depends on mission 2. So if I don't select mission 2, I cannot select mission 11. And you will see that this constraint guarantees that. Okay, so if X2 is 0, mission 2 is not selected, then X11 must also be 0, i.e. mission 11 is not selected. If X2 takes the value 1, then X11 can also take the value 1, indicating that the 2 missions are selected. And we have a similar structure for missions 4 and 3, missions 5 and 3, missions 6 and 3, and missions 7 and 3. Finally, you see the binary requirement for each of the decision variables. So this particular problem is known as a multi-dimensional knapsack problem. I'm sure you've encountered the knapsack problem before. That models a situation in which you have a knapsack, well, at least metaphorically, you have a knapsack. You have a set of items you can choose from. Each of these items has a profit and a weight. If you select the item, you gain its profit, but the weight of the item will also consume some of the capacity of your knapsack. Okay, and in this case, we have 5 knapsacks. Pretty much, we have 5 budget constraints. We have 1 for each of the planning periods. We have 3 packing constraints, as I said, to model the incompatibilities, and we have 5 other constraints to model the dependencies between missions. If you solve this problem, you will find that the optimal solution has a value of 765, and that we run missions 1, 3, 4, 8, 13, and 14. Okay, so this is the solution that we will use when we sort of try to assess the performance of our greedy heuristic. This is the optimal solution. We cannot do better than this, and we will see where we land in terms of an objective value when we design the greedy heuristic. Okay. The following Julia code can be used to find the optimal solution to the binary integer program that we just formulated. I'm not going to spend too much time on it. I'll just give you the highlights. We start out by declaring a model. Here I store the problem data in 3 different arrays. The value for each mission is contained in the profit array here. The weights array contains the budget consumption of each mission in each of the 5 planning intervals. So this 6 here corresponds to the $6 billion that mission 1 would consume if selected. Okay, it would consume $6 billion in the first of the 5 budget intervals. So there is a row in this array for each mission, and there's a column for each budget interval. The budgets array down here gives me the allowable budget in each of the 5 planning intervals. Down here, I declare the 14 binary variables in my problem. My objective is to maximize the value of the selected missions. I build the 5 budget constraints here. There you see the constraints ensuring that I don't select incompatible missions, and down here you see the constraints ensuring the dependencies between the missions. So if you run this, you will get the solution we found on the previous slide. Okay, but now let's design a greedy heuristic to solve this problem. The greedy heuristic is going to be an iterative approach, and it will successively add missions to the solution until the constraints prevent us from adding any more missions. It makes sense that we will prefer missions with a high value, since these are good in terms of the objective value, but it's not the only thing we will consider, okay? Just because a mission has a high value doesn't necessarily mean it is good. It might consume too many of our available resources and prevent us from including other missions. So we would like to sort of try to capture both of these things here, high value and resource consumption. Selecting a mission at a given iteration is going to secure its value, but it will naturally impact our future choices. It's going to use some of the available resources and therefore limit future choices. We're going to try and incorporate the dependencies in a mission's implicit value. So we want to be able to prioritize missions that enable other missions. So we would like some way of including a bit of extra value in a mission's value just to indicate that it opens up other missions. So the missions are going to be selected based on comparing mission-specific ratios, and these ratios will attempt to capture this trade-off between the objective return that we get and the resource consumption we lose. Okay, let's take a closer look at how these ratios are computed. Here Rj refers to the ratio for mission J. It's computed as follows. The numerator reflects the value of the mission, and this is comprised of two different aspects. The first part is mission J's value, so how much do we get if we schedule mission J? The second part is an allowance we add if mission J enables other missions. As I said on the previous slide, we would like some way of distinguishing between missions that enable themselves and missions that enable other missions. So by adding this allowance, we maybe add a small reward for missions that actually give us access to more missions. The denominator here is capturing the resource consumption by scheduling mission J. So we look at the first 8 constraints because these are the 8 constraints that have a non-zero right-hand side. And we look for each of these constraints, we look at the fraction of the remaining amount of the constraint that is consumed by mission J. We add these up, and this gives us an indication of how much of the remaining resources mission J will use. Okay, here it's just stated a bit more mathematically. Cj here refers to the objective coefficient. The allowance we add is half the value of any mission that is enabled by mission J. Adding half the value of these missions that are enabled is an arbitrary choice. There's no golden rule for this. This is something that we think is intuitively a good idea, but we have just settled on this arbitrarily. The denominator here sums over the 8 constraints, as I said. It looks at the resource consumption in each of these constraints for mission J, and BIT here just states the remaining resource in constraint I at iteration T. Remember, the greedy heuristic is an iterative approach, so we will make a selection initially. We will then reduce the resources that the selected mission used, and on the next iteration, we will have fewer resources available to schedule new missions. This slide just provides a summary of the things we've been through regarding the ratio, at least. The numerator tries to capture the immediate value of the mission and the potential value of any dependent missions. As I said on the previous slide, we arbitrarily add half the value of any mission that is enabled when computing the ratio for a specific mission. There's no golden rule to follow here. Intuitively, we think this is a good idea because it would allow us to distinguish a little bit between missions that enable themselves and missions that enable other missions. But there's not really any indication that this is the best thing to do right here. And the example is designed to show you that although you think you're building in reasonable logic, you can't capture everything. And you will see from the results that this may not even be a good heuristic for this problem. The denominator is summing the fractions of the remaining resources that a mission would consume if selected. And of course, we favor missions with a high ratio. They're giving us the best, what's called bang for buck in the objective. So per unit invested, they're giving me the best return. So just to summarize how this greedy heuristic works, at every iteration t, we will choose among the unassigned missions for which all sort of dependent missions have been scheduled in the partial solution, and we're going to fix the value of xj. If there are enough resources to schedule that mission, we will assign it the value 1. Otherwise, we will set it to 0. So let's look at some of these iterations in detail. I'll try to go through it a bit quickly. It's very repetitive, but it will give you an idea of how this construction algorithm is working. So initially, all of the variables are unassigned. So x is our vector of decision variables. There are 14 spaces here, 1 for each of the missions. 0 just refers to the fact this is the 0th iteration. At the beginning, all right-hand sides are equal to the initial right-hand sides. We haven't scheduled anything. And 2 ratios are computed here for you. So the ratio for mission 1 is computed as 200 divided by 6 over 10. 200 is the objective return for mission 1, and 6 over 10 is the fraction of the remaining resources this mission would use. And this gives me a ratio of 333 1/3. Mission 2 is a little bit different to mission 1. We get the value of mission 2, but we also add half the value of mission 11 because mission 2 enables mission 11. The fractions of the remaining resources mission 2 consumes are down here, and this results in a ratio of 26.57. Okay, so based on the ratios, mission 1 is sort of more attractive. It's giving me the best return and the objective per unit invested. All of the ratios are given down here, and we look at the ratios. We identify the one that's the largest. In this case, it's mission 13, and we set that variable to 1. So now we've done one iteration. We've selected a mission. We update the solution so that it now includes mission 13. We update our right-hand sides to now reflect that mission 13 has been selected. So we deduct from the budget constraints the budget that mission 13 uses, and then we recompute the ratios. So down here, we can no longer select mission 13. It's not available anymore. We've already selected it. And in this case, mission 1 has the highest ratio, so we select mission 1. So now 2 variable values have been fixed. We update our solution vector to include mission 1. We update the right-hand sides to reflect that now mission 1 and mission 13 have been selected, and we recompute the ratios. We now look down here to find the ratio that is the largest. In this case, it's mission 10, and we add mission 10 to the solution. Okay, so now we've done 3 iterations. 3 variable values have been fixed. Our solution contains mission 1, 10, and 13. We update the right-hand sides of our constraints. Sorry, I probably should have said earlier that the first 5 of these constraints are the budget constraints, and the next 3 constraints correspond to the incompatible missions. So one of these constraints, its right-hand side would decrease to 0 if I scheduled one of the incompatible missions. So now, based on this solution and these right-hand sides, I compute the new ratio, and I see that I want to select mission 9. It has the largest ratio, but there are not enough resources left to schedule mission 9. I think it uses something like 5 billion in one of the budget constraints, and we only have, I think it's 3 left here. Okay, so I can't assign that mission, so I set its value to 0. And in fact, then there are a whole sequence of iterations where you cannot select a mission due to insufficient resources. And now we get to iteration 9. We still have only selected 3 missions. These are the right-hand sides, and these are our ratios down here. The highest ratio sort of belongs to mission 11, but I cannot select mission 11 because in my partial solution, I do not have mission 2. So I select the mission that has the next highest ratio, and in this case, it is mission 2. So I will select that and fix it to 1. I'll update the solution to include mission 2. I'll update the right-hand sides to reflect that mission 2 is now also selected. I will recompute the ratios. And down here, I can now select mission 11. It has the highest ratio. Okay, and then I'm done. Okay, and there's no other missions I can select. So I would terminate now with a solution of mission 1, mission 2, mission, is it 10, 11, and 13, giving me a total value of 675. And if I compare this to the optimal solution, remember it had a value of 765, there is quite a difference there. So the greedy algorithm in this case clearly returns a suboptimal solution. And if you look at the 2 solutions, you'll see there are some differences, right? In particular, the optimal solution does not include mission 10. And that was something that we put into the solution very early in the greedy approach. And this sort of illustrates that although you are taking, based on your greedy selection strategy, you are selecting locally to the iteration the best improvement in the objective, this does not lead you to the globally optimal solution. Okay, so globally optimal means there's no other solution better than that solution. So despite the fact I'm making solutions that optimize my greedy selection strategy, I ultimately end up with a suboptimal solution. That is the sort of important takeaway here. However, are there occasions when a greedy approach actually returns the optimal solution? The answer to that is yes, and that is going to be the focus of the next part of the lecture. But this ends the first part of the lecture.